which focus on ocean circulation and have been referenced a combined number of 2,200 times. These papers have given direction to our field as well as accelerated the distribution of knowledge to new scientists. Today, he will give a talk titled Meridional Heat Transport in the Ocean and Atmosphere. Please let's welcome Professor Ferrari. Thank you very much.
Thank you. Thank you. Yeah, now it works. We are getting halfway through the marathon of this series of lectures. I don't know if it feels a marathon to you, but it does to me. And in the first two lectures, we really focused on large-scale circulation in the ocean and the role of that. We might discuss probably later today, what I would call microturbulence. It was breaking waves on scale of order of 10 to 100 meters in the ocean and how they affect large-scale circulation. Today, we are moving to larger scale in turbulence that still have a very large impact on circulation. In this case, we're not restricting only to the ocean, but also to the atmosphere or planetary atmosphere in general. So it's supposedly a pretty fundamental properties of fluids on a planet that are subject to rotation and the changes in density, so stratification. And the problem, well, the question is pretty well known. Now if I point here, however, they don't see there, right? So, oops, something happened here. There it is. You see the pointer, yeah. So if we consider a planet like the Earth that receives more radiation in what you would call the equator than at the poles, then there is a profile of incoming radiation that you see from the right. It's this outer curve. This is the radiation arriving to the planet at the edge of its atmosphere. And so it receives more radiation on the equatorial line than it does at the pole just because of the sphericity of the Earth. If you assume that there is a star far away that is shining in over it. Now, if you look at and it's in particular, here's real data observed from satellite at the top of the atmosphere. If you look at the radiation that's coming out of the planet, it's this other curve that is above the incoming radiation curve at high latitude, that is below the radiation curve at low latitudes. What it means is that the system is emitting less radiation back to space at low latitudes than it is receiving, while at high latitudes it's emitting more radiation than it is receiving. So in order to accomplish that, there must be motions in this, if this system has fluids like our atmosphere, ocean and atmospheres, that transport heat from the low latitude where there is an excess energy received to high latitude where there is an excess energy released to space. So what we want to understand is what sets the rate at which heat or energy is transported from low to high latitudes, because clearly that is what's going to set in the end the climate state of that system, meaning the temperature distribution with latitude, for example. This was working before. Okay. In particular, for the Earth itself, we can actually look at what contributes to that heat transport. So now this is the heat transport, how much heat transported from low to high latitudes. It's positive, this is latitude, so this heat transport is positive in the northern hemisphere, meaning that heat is transported towards the pole. And it's also negative in the lower hemisphere, meaning that the heat is transported to the south, meaning again towards the poles. This is the total heat transport, peaking at something close to 5.5 petawatts in both hemispheres. And what you see in the dashed line is the contribution to the heat transport by the atmosphere. So the atmosphere dominates overall in that heat transport, is more efficient at transporting heat. Then there is a contribution by the ocean, in particular in our Earth system, because those are the two fluids that can efficiently move heat. Across latitudes, the ocean typically dominates, especially in the northern hemisphere at very low latitudes. But the point I want to make more is here, why do we care about something like this, is that we could estimate the temperature budget or the surface temperature of an atmosphere in what is called the radiative convective equilibrium by assuming that there are no motions neither in the ocean nor in the atmosphere, and look at what is the temperature distribution you would get out of that system. And this is the surface temperature distribution that would be in excess of 40 degrees Celsius in the tropics, so pretty hot, and this is a nearly average. and everything essentially north of, I don't know, 38 or 39 degrees would be sub-freezing temperature on average. So in winter, we'd be way below that. Maybe that doesn't seem shocking for Toronto, but you probably under a lot of ice in a climate like this. Instead, because of heat transport, you reduce a lot the temperature gradient. So it really, the presence of this motion in ocean atmosphere really dominates or fundamentally change the surface temperature that you observe in this climate. Now, the question is, what achieves that heat transport? And we can start by looking, here is potential temperature at 850 millibars on our Earth. This is the US continent. And we're just going to play a movie. And what you start seeing, the color is the temperature itself. Oh, it doesn't play. The color is temperature. So you see cold is blue over the Arctic and warm is towards the equator. And what you see is that while there is a mean temperature difference between the two, you see a lot of what are called cyclone and anticyclones that act again, like we discussed yesterday, like spoons that mix cold and warm water. These are the storms that we experience as weather. And they're really redistributing and trying to transport some of the heat to high latitudes and some of the coldness to low latitude. And that's how the heat is transported. We can actually quantify that. This goes back from, it's been well established. This is from a textbook by Peixoto and Ort in Physics of Climate, just trying to make the case or just show us. I try to convince you that it's this cyclone and anticyclone that transport the heat. Actually, we can make this a bit more quantitative. The heat transport is just the velocity times the temperature multiplied by the heat capacity of water, of air in this case, times the density of air. That's the total heat that is transported. And I want to integrate it in the vertical, well, and actually I should have written also that I'm integrating also along a longitude circle, just to see how much heat is transported from one latitude to the next. And I can split that average in two components. One is the product of the mean velocity times the mean temperature, and what by mean I here mean temporal mean and a zonal mean. So this is the mean circulation. If people know the structure of the circulation in the atmosphere, for example, that would be your Hadley circulation, that large scale circulation that exists in the mean at all times. And the other term is instead a departure from that mean, which is associated with transient motion that either in space or time are fluctuating. And so if you look at again at the heat transport, this is only for the northern hemisphere, pretty much starting from 0 degrees north to 75 north. And you see again this heat transport peaking out. This is only the atmospheric component. It picks up here at something like 3.5 petawatts. That is not the main point. And now what they do is that they decompose the heat transport in this curve, which is the mean heat transport. And this dashed line is this what called eddy heat transport. We're going to call the macro turbulence, the transient eddies, the cyclone and anticyclone. And it's just to convince you that most of that heat transport is transported actually by this macro turbulence, not by the mean circulation, except at very low latitudes where the mean circulation might dominate. And we'll probably discuss in a second why that is. The eddies dominate so much that there are latitudes in which the mean is actually transporting heat in the wrong direction from the point of view of the energy balance, meaning it's transporting heat towards the equator instead the other direction, but the eddies of this macro turbulence is so strong that winds over and the heat is indeed transported towards higher latitude in the net. So it looks like if we want to understand heat transport in, or the net heat transport in an atmospheric system, we really have to pay close attention to this macro turbulence. Where does this macro turbulence arise from? And this is a nice movie that is on Tapio Schneider webpage. What they do is, now you're looking at a numerical simulation, like the data before. This is height and depth in the atmosphere. This is latitude. And what you're looking at is, and this is meridional velocity, the zonal velocity in that system. This is the two big jets, the mid-latitude jets. But the way they constructed the solution is they start again with a convective equilibrium solution, like you're not allowing any lateral motion to develop initially. You just look at what is the temperature distribution, and then you assume it's in thermal wind balance. So you reconstruct your vertical velocity field, and you get these two jets, and the temperature is warmer at the low latitudes and colder at high latitudes with a very large temperature gradient, because you didn't allow lateral motion yet to develop. Thermal wind balance is a solution of the Navier-Stokes equation. So this is a steady solution. The question is whether it's a stable steady solution or not. And let's see now if this works. Well, it worked, but. Okay. So I let this system evolve. And what you see is that this system hasn't really perturbed really or anything, just small tiny numerical noise. And you see that the system goes unstable spontaneously. By the form of instability is called Baroclinic instability that is associated indeed with a lot of meanders in these mid-latitudes that mix heat across latitudes. And if you look at the temperature profile here, it's become, the temperature difference has really diminished because of the emergence of this macro turbulence that essentially has mixed heat across latitude, reducing the mean temperature gradient. Just to show that this doesn't happen only in the atmosphere, so it's a generic problem, we can look at the ocean as another case. This is a sector of the Southern Ocean off the coast of Australia. So Australia is up there in the corner. And what you're seeing is, again, sea surface temperature. This case is the ocean, not the atmosphere. You see, again, warm towards high latitude and cold towards lower latitude. So there is this large-scale temperature gradient, but you have a lot of what are called geostrophic eddies that develop in this ocean that acts in the same way as in the atmosphere. The big difference, as you can tell, is that the eddies here are much smaller scale compared to the scale of the flow than in the atmosphere, where those eddies were close, not close, but a good fraction of the planetary scale. The main reason for that difference is that the ocean is made of water, which is much less compressible than the atmosphere. So it's really the compressibility coefficient, how much temperature affects density, is much stronger in the atmosphere than it is in the ocean. And that therefore you have effectively larger density difference in the atmosphere from a dynamical standpoint. So that makes the scale of this motion smaller, but they still act in the same way. When you look, they again are like smaller spoons that mix across the temperature profile. You can expect that since they are smaller spoons, as a result, they are less effective at mixing across heat. So the ocean is less effective at transporting heat across latitude, which is what we've seen before. And most of the heat transport is really associated with macroturbulence in the ocean, not macroturbulence. Macroturbulence in the atmosphere, not macroturbulence in the ocean. Again, also in the ocean, we can, in particular in the Southern Ocean, this portion I'm focusing on the Southern Ocean because that's the only big re-entrant current we have where you really have this zonal flow and its instabilities, but the same would apply if you look at other currents like the Gulf Stream or the Kuroshio. But again, in the Southern Ocean, we can make this budget. Clearly, again, we can divide the heat transport by the mean circulation versus the heat transport by this macro turbulence that emerges, all these eddies that are emerging in the flow. In that picture you haven't seen, but there was also the big ACC current moving east to west, right? So if you look at the heat transport, meridional heat transport across latitude, so this is latitude and this is my heat transport. This is the heat transport by the mean circulation, which in the ocean is primarily driven by the winds. And you see that interestingly enough, it's positive. Here we are in the southern hemisphere, so positive means the heat is transported by the mean circulation from the pole to the equator. So the mean circulation is trying to make the equator even warmer than it would be without motions in the fluid. But again, there is this macro turbulence, all this eddy that we see in the transport heat in the opposite direction. Here they are split in two components. It's what are called standing meanders versus transient eddies. And there are eddies that appear and disappear, but in the ocean and in the atmosphere, there are also just big standing meanders in the flow that continuously distribute heat without changing in time, but just their departure from the zonal average in a sense. In any case, you should by eye sum these two lines to get the full effect of the macro turbulence. And when you sum the blue and the red, you find this black line, that's the total heat transfer, which is actually negative. So it means that the eddies are strong enough when you sum their contribution, the macro turbulence is actually transporting heat from low to high latitudes. So it's a thermally direct system that is trying to cool the equator and warm the poles and reduce the temperature gradient. So it looks like when you have a system that have this potential for baroclinic instability, that's very effective at redistributing heat. And again, we can show the last movie just to show how this happens in an ocean state. So now this is, again, a numerical simulation of an ocean, which is stably stratified. This is depth. And you can think about this as being a model of a sector of the Antarctic circumpolar current. So we're going to have winds blowing from west to east. Again, our roaring 40s or screaming 60s coming this direction. These winds will take this temperature distribution and they create, as we said yesterday, a convergence of flow. And so they'll try to push warm water into the fluid. So you see that the density surface will start tilting in response to this wind that creates a convergence and pushes water into the interior of the fluid, and instead it will upwell water here. So you're really generating a circulation of this kind, which, by the way, explains, so this is latitude, right? So this is Antarctica, and this is towards the equator. So if the winds generate a circulation that goes to the left of the wind pattern, well, you're going to get flow that is essentially clockwise. So it's transporting heat, warm water towards the pole, towards the equator, and cold water towards the pole. That's why the heat transport is in the opposite direction, what you might have expected. So what you see is that the circulation will tilt isopycnals. As the isopycnal tilt, you're creating a horizontal temperature gradient. As soon as you have a horizontal temperature gradient, you're going to develop a current in geostrophic balance that is from left to right. That is your Antarctic circumpolar current. And then we see that again, it goes unstable to Baroclinic instability, and we try to flatten the isopycnal to reduce the temperature gradient again. So let's see that what happens. Now you see that the wind started blowing. There is also some cooling, warming and cooling pattern. Well, technically it's heat loss or brine rejection, salt that enters into the ocean and makes it denser. Here it's instead precipitation makes it lighter. And now you see the density surfaces are tilting downward here, and you start seeing the emergence of some of these eddies, the macro turbulence. They will become more and more vigorous as we move forward in time. And now you have a strong turbulence that it's opposing the mean circulation, is transporting heat, mixing this warm water with the cold water here. And so it's transporting heat towards the pole, and it's so effective that it dominates in the net budget of the heat transport. So any theory of a climate system for a planet that has an ocean or an atmosphere requires some theory for what is the transport of heat by these turbulent eddies, because they dominate. Just to show that this is not a problem only as far as we understand in planetary, in the Earth, atmosphere and ocean, it's a problem that happens in other planets with atmosphere. If we look at the surface of Jupiter again, you see a lot of these macro turbulent eddies that are mixing properties across latitude in the same way. Interestingly enough, because of its size, the size of the eddies in Jupiter look more like the size of the eddy in the ocean. So dynamically, Jupiter is closer to an ocean than an atmosphere in our system, just that the scale of these eddies that we see is not too far from what is called the deformation radius, when in the Earth, the deformation radius of the atmosphere is close to the planetary scale, but not in Jupiter and not in the ocean. But that turns out not to be a fundamental difference in how we have to describe the ocean, but what I call macro turbulence. And now just a word to say, since we had two lectures where I was talking about turbulence in a very different context, I want to explain what I mean by macro turbulence versus micro turbulence, which is what we talked about in the last few days. On the left, I have an example of what I would call macro turbulence. So we have now a system like the ACC in the ocean, or you can think about the jets in the atmosphere, the mid-latitude jets in the atmosphere. So we have two fluids, dense and light. This shows that the potential temperature is decreasing with height, and there is a tilt. The tilt in the atmosphere is due to the fact that you're cooling at high latitude. So in the average sense here, you have more cold water, cold air than you have on this side. So this is colder than this side. So in that case, it will be the heating and cooling pattern is tilting your density surface. That's the forcing of the system. In the ocean, instead, it's wind that would push water down here and up there, and so it creates a tilt. So that's what provides energy to the system. Now the system goes in thermal wind balance. So you have a jet coming at you in the upper part and going into the page. And then, as we said, Baroclinic instability naturally develops in this system, but it's important to check what is the Richardson number of this system, which is just a ratio of the stratification, the change of density with height, divided by the shear associated with this flow. And it turns out that the Richardson number for large-scale flows in the ocean atmosphere is much larger than 1. So Baroclinic instability is the dominant form of the instability for this large Richardson number. And what it does is what I show down here, is take this tilted surface and just flatten it out. But it never mixes any properties from the cold water into the warm water or vice versa. It's only slumping the density surface without mixing across. So that's what we call macro turbulence. It's a turbulence in a sense, it's adiabatic. It rearranges water parcel, but without ever mixing two water parcels together. That's quite different from the situation that arises on much smaller scales, like the ones that we were discussing yesterday. Again, I can have a fluid that is warm on top of a fluid that is cold, Now I have some shear in the direct parallel to the density stratification. If the shear, again, if I compute the Richardson number, the stratification divided by the shear in the case of an internal gravity waves, for example, in the ocean, the shear can be large enough to make the Richardson number less or equal to some order 1 value. In that case, you have instability that create what are called Kelvin-Helmholtz billows or instabilities of that form that start mixing fluid across this interface. So this is what we would call microturbulence, but this is the macroturbulence. So the last day we talked about how much you mix across density surfaces. Now we're going to try to look at how we transport properties laterally without mixing across density surfaces. That's the second aspect of turbulence that is particularly important in the ocean, but it's also important in the atmosphere and in planetary atmospheres in general. So the turbulence, this motion is generally much larger scale, and this is much smaller scale. It's only smaller scale that have very small Richardson numbers. And if you're interested in this kind of distinction, Dick Pertier, who unfortunately cannot be with us today, but contributed a lot to that literature on the effect of small Richardson number instabilities in geophysical fluid dynamics. So if you want to study this macro turbulence, it's generally a good idea to try to find, since, as I said, it's a subset of all turbulence that could happen in GFD. We want to find the subset of equations that capture that instability without having to deal with the whole set of dynamics that could happen in the Navier-Stokes equations. And it turns out that we can rely on our founding fathers. I guess some of them have given previous Nobel lectures. Isaac Held would be obvious name, who, building maybe on even their founding fathers, Jules Charney and Eddy, that developed a subset of equations which are called the quasi-geostrophic equations that indeed capture the dynamics on large scale. So they're a filtering of the full Navier-Stokes equation that filter out gravity waves that can create this more Richardson number or internal waves in general that are higher frequency motion and just keeps the low frequency motions in the dynamics. In particular, it turns out that we can use a particular subset of the quasi-geostrophic model, just a 2-layer model. So we have representing the whole ocean and atmosphere as 2 layers of fluid of different density, lighter density above and higher density below, and an interface in between. It turns out the most large-scale motion in the ocean and atmosphere are really captured by this low-order model. So for the macro turbulence we want to describe, it has enough of the dynamics that we need to investigate. The 2 layers are going to have some mean depth that I call h/2. So the full depth of the fluid or of the atmosphere or the ocean here is capital H, and the mean depth is h/2. But then this interface can move up and down when motions develop. And we're going to call that departure small h. So small h is the departure or how thicker this upper layer is. Another parameter that we'll enter is the G prime, which is just the relative density difference between the 2 layers, right? ρ2 minus ρ1 divided by ρ2. So it's the fraction change in density multiplied by G by gravity. So that's essentially the gravity that this fluid is feeling at the interface, because it doesn't feel the full gravity because there is just a small density difference between the 2 layers. Maybe there is going to be another parameter that enters the problem. We'll explain in a second what it actually characterizes, but let's start introducing it. It's the Rossby deformation radius that depends on this G prime, depends on H, but on top of it, our system is going to be rotating. And indeed, the quasi-geostrophic approximation, I keep insisting that applies for large-scale dynamics, but also for low-scale dynamics. Those scales much lower than the rotation of the planet. And so indeed, there is a parameter, this parameter depends also on F0. So these are the 3-dimensional parameters enter in, and this is a length scale that emerges from that. It's a characteristic of the system. For the moment, we don't know exactly what it represents, but it depends on the set of parameters entering in this problem. Now, how do you describe the dynamics of this system? It's actually interesting that it can be described, and here, we don't know who is in the audience, otherwise there are people that could become very nervous or not, depending on how they like it. You can describe the dynamics as conservation of angular momentum in the upper layer and then the lower layer. What I mean by that is that think about an air column in the upper layer, and we are stating that it has to conserve its angular momentum. If it has to conserve its angular momentum, well, it has to conserve its relative vorticity, the spinning around its axis, and then it has to conserve its mass. So it can be stretched or thin, but as a result, it becomes larger or thinner. So let's see what it means to insist that I want to conserve the angular momentum of air column in each layer. Well, the first thing is that if Q1 is my proxy for angular momentum, it has to be conserved by lateral motion. So I can take a water column, and are people familiar with the notation J? That's a Jacobian. What this is just, if you want U dot grad Q, it's just the advection of this Q quantity by horizontal motion in each layer. And there is a U1 in the upper layer and U2 in the lower layer. Or if you want, psi1 is the stream function in the upper layer and psi2 is the stream function in the lower layer. Right? So an air column is advected by motion in each layer. So that's fine. And it has to conserve its angular momentum. So I'm just saying that dq1 dt is equal to 0. That's essentially by advection. So Q1 is conserved if I follow the water column as it moves around in the fluid. In the lower layer, that's not quite true because there is going to be some bottom drag because the air column rubs against the earth, or in the ocean, there is also some bottom drag because there is bottom topography. But now let's look at what Q1, when I keep insisting Q1 is my angular momentum, where it's composed of two terms. This is the relative vorticity, if you want to think it's the angular velocity around your axis. So indeed, you have to conserve that. But there is a second term that depends on the difference of the stream function. Well, in the quasi-geostrophic approximation, that term is just h, the thickness of the layer. And it's a bit like the skater, right? If the skater is bringing their hands closer to their axis, they're going to make h increase. So this term goes up. In order for Q1 to be conserved, they have to spin faster. So the relative vorticity has to go up. So that's just the angular momentum. And you see that you can trade off relative vorticity, the spinning around your axis, for changes in the thickness or in on the moment of inertia of that air column. And the same applies to the lower layer. So you have these two layers. This is a change in sign here because an increase in h here means a decrease in h in the lower layer because the two layers are connected to each other. It turns out that this stretching term is crucial here, right? Because these two equations, if I didn't have any stretching term, if I didn't allow that interface to move, well, the two layers would move independently of each other because this equation wouldn't depend in any way from the lower layer and vice versa. It's the stretching term that allow angular momentum to be exchanged, well, not strictly exchanged, it's momentum that is exchanged between the two layers. So this is the full dynamics of the system. Now you see that since the relative vorticity just can be expressed in terms of a string function and the stretching can be expressed in terms of a string function. If I plug now these terms or substitute in this equation now, the two equations are equation just in terms of the string function is a closed system. I can just evolve it forward in time. And it's a much simpler system, the full Navier-Stokes equation in just two equations in two variables, these two string functions that describe the full evolution of the fluid. As a remark, H, I'll be a bit loose in what I refer to. I can refer it as layer thickness or as temperature. Why do I call it a temperature? Well, because if you think about it, when H is a bit thicker than usual, it means that there is more warm or light fluid in this layer and less in the lower layer. So in a vertical integrated sense, that part of the fluid is a bit warmer than average. If H is instead negative, it means that there is more dense fluid than light fluid or more cold fluid than light fluid. So an increase in H can be thought about an increase in temperature. A decrease in H is a decrease in temperature. So you can call it H and a temperature-like equation, a temperature-like variable. So this is the system of equations we want to use. And now we want to use them, or put them to use, to study the evolution of a jet or a system that has been forced and has a temperature gradient north to south. What I mean is what I was describing before. Like now, this is my box again. It's the two layers of fluid, light, and dense. But now I'm going to impose that there is some tilt of this interface. This is going to be my latitude. So in this case, this will be the north. This will be the south. So here there is more cold water or cold air than light air or warm air. And here there is one warm air. So you see the temperature gradient. And this is what is maintained, as I said before, either by radiation in the atmosphere or by winds in the ocean that tilts that interface and keeps it up. This velocity is going to be in thermal, this tilt in the interface is going to be in thermal wind balance with a mean velocity u. So what I'm going to contend is that there is a basic state that I impose, which is represented this large scale forcing. And that basic state has a velocity plus u in the upper layer, minus u in the lower layer, right? U is minus d psi1 dy, so this becomes plus u. And then there is a perturbation psi1 and psi2 that we're going to study in a second. And since the system is in thermal wind balance, that implies that there is also tilt in the interface, which is given here. So that the velocity u minus u is in thermal wind balance with this tilt in the interface. So now I can start with this system, and I'm going to put in a W, well, we'll get in a second what I do with it, but now I have my mean state, and what I want to ask is, if I have that mean state and I give it a tiny perturbation, do spontaneously instabilities emerge, or the system just pretty much sits in this stable position? That is just asking whether that solution is a stable solution. It is clearly an equilibrium solution, but whether that equilibrium is stable or not. It's a bit like having a ball on top of a mountain. Right on the top, it might be in a stationary, it might be an equilibrium solution, but as soon as you kick it, it will run away. Versus a ball which is in a valley. So if I kick it a bit, we just sit around the equilibrium. We want to ask, is this system close to a ball in the valley or on top of the mountain? And as you might expect, it's like being on top of the mountain. When I kick it, I expect it to go unstable to something that is called the Baroclinic instability. And finally, this deformation radius comes. This is one of the two critical parameters in this problem. The instability turns out to create meanders along this jet on the scale, on scales close to this deformation radius. That's why this scale becomes quite important. And the second external parameter now that we really introduced that has to do with our basic state is this U, if you want to call it the shear of the flow. So we impose the shear. So these are the two non-dimensional parameters, the two-dimensional parameters that would be particularly important in this problem. We impose the mean shear, and there is a deformation radius which characterizes the structure of the two-layer problem. Now, if I run a numerical solution, I can put this solution in a doubly periodic system. Turns out that when I prescribe that mean state, I use linear gradient in my mean state. So when I put, since the mean state appears only as derivatives in the equation I have, when I take derivative in y, they become constant. So my equation has just constant coefficients. If I have an equation constant coefficient, I can put it in a square box and put periodic boundary condition, because I can use Fourier transforms in that system and just solve the system in that box. And I'm just showing solution of this system. There is a basic state, turbulence emerges, and I'm going to use over and over in the talk, instead of the stream function in the upper layer and the lower layer, I generally use the barotropic stream function, meaning the average stream function, the sum of the stream function in the upper layer plus lower layer divided by 2. You can think about that as the vertically average velocity in the flow. And the other one instead is the Baroclinic stream function, which is psi1 minus psi2 divided by 2. The difference in velocity between the two layers, but if you remember, that is also proportional to h, the thickness in the layers, or as I said, you can also think about it as the temperature. In order to equilibrate the system, we are putting some drag in the bottom because the turbulence emerges, but it would keep pushing energy into the system because in a sense, we have an infinite amount of energy because we don't allow that basic state to ever relax in this problem. So the energy keep growing and piling up in the system. So we need to have a way to extract energy. And we're always going to consider two cases. We can have a linear drag in the bottom layer, just something that slows down the flow, a bit like what I used yesterday in the flow over a slow problem. Or you can have a quadratic drag. This is generally defended more in terms of Ekman layer dynamics. Ekman layers at the bottom of a fluid would act a bit like a linear drag. This is more like quadratic law, is more a turbulent flow that would develop at the bottom. If you really had some unevenness at the bottom of the atmosphere, just some friction, you would expect to get some quadratic damping, meaning that the stronger the velocity, the stronger the brake that is imposed on the flow. But this represents essentially turbulence at a smaller scale than the quasi-geostrophic dynamics cannot resolve, but they suck out energy out of the system. So if I let the system run to equilibrium, these are the kind of solution I get. Here I'm really looking at vorticity. So if you want the angular velocity of particles in the fluid, you see that this system is characterized by a set of vortices. They're pretty dilute. We're always going to look at limits where friction is pretty small. So it's not entering and damping at the scale of this vortice. It's acting, it's a small damping coefficient, so the system can become sufficiently energetic. But it's what we would call, and we come over and over, as a dilute gas of vortices, meaning that there are vortices, they are pretty small scale, and they are separated by a scale that is much larger than their radius. So they are floating around. You can think about a dilute gas of particles where there are collisions, but they're not that frequent. Instead, when you look at the temperature, well, the scales are larger, but in particular, you see there is a lot of background flow that are clearly peeling off of temperature being transported across latitude. So probably there is a heat transport in this system because I have a velocity field and I have a temperature, and the velocity field can affect my temperature-like variable. Yeah. So here we're really imposing that mean state. So the mean state is prescribed, it cannot change. Which we'll get to it. No, we'll get to it, because indeed this is a limit in the sense that, right, in the atmosphere, I told you when we looked at those simulations that eventually what that turbulence does is to relax the temperature gradient and reduce it. For the moment, I'm not allowing that to happen. I'm just asking, well, if I know what is the mean temperature gradient at equilibrium, what is the strength of the heat transport that exists in that system? We'll move at the end of the talk in allowing that temperature gradient to relax, so we put some forcing and then we do the full problem. For the moment, we do a simpler version where we're just asking, well, if it is an equilibrium, if I already knew what is the mean temperature gradient of the atmosphere, and I just let it go, what is the strength of the eddies that are required to maintain that equilibrium temperature gradient? Now, just for the fun of it, I mean, I decided that, well, part of the inspiration for this work was indeed literature that was put forward by Rick Salmon and Isaac Head, the former lecturer, as I pointed out. They were trying to study indeed this problem and took an approach that goes all the way back to Kolmogorov in studying turbulence. In his case, he was studying micro turbulence. So micro turbulence was so small scale that it doesn't even care about stratification. But I think I'll try to make the case that I'm not sure we are looking at the problem in the right way. So first I'll introduce the way this problem is typically looked at, and then try to go back to this dilute gas and explain why there might be a more promising way of making progress on this problem by looking at it from a different perspective. And I'll try to convince you why you actually start understanding properties of the flow that seemed pretty mysterious before. So the way generally this is described, and this is from a very famous proceeding in the Enrico Fermi School in Varenna. I don't know if they still run them. If they do, I encourage any student postdoc to go. It's a wonderful place, and it's definitely worth for it, also for the science, but also for the food and the scenery you get to see. This was in '82, and this picture has become really, I mean, this is an updated version of the picture that Rick produced, but it's become a bit of canonical description. So the idea here is that this axis supposedly represents the baroclinic energy in the system as a function of scale. So this is the large scale, this is the small scale. So you can think about, you know what a spectrum is, the distribution of energy as a function of wave number or as a function of scale. And this is the part of the energy that is baroclinic. So the energy associated with the difference in velocity between the two layers of the fluid, or if you want, the thickness of the fluid. And this lower axis instead is the barotropic energy from large scale to small scales. The idea is that forcing generates baroclinic energy. Why does it do that? Well, because we said that the forcing is what tilts the interface of the fluid, and that is the baroclinic component. Right? It's changing the mean H, and it does it at very large scale. It's forcing on planetary scale in the atmosphere or forcing on large scale in the ocean. Then when that system starts, these are the movies I've shown you, the system goes baroclinically unstable, this large scale at the scale close to the deformation radius. So the idea is that all of a sudden, all this baroclinic energy starts generating turbulence, and a lot of that turbulence generate barotropic eddies. We've seen in the movie that you have these vortices that are barotropic, so you generate a lot of this barotropic energy. Now there is a big statement here that is validated in theory, is that these eddies start interacting and supposedly they pair and they form larger and larger eddies, so they transport energy to larger and larger scale until they are large enough that they experience some dissipation, substantial dissipation, and they get eliminated from the system. So there is a description in spectral space where you have energy that enter a large scale, is converted to barotropic energy at small scale, and then it's again dissipated at large scale. So there is a transition from baroclinic to barotropic energy and an inverse cascade of energy that has to be pushed up to larger scales. There are people that are more fluid dynamicists. That should be a bit of a surprise, because generally in three-dimensional turbulence, without constraint of rotation and stratification, generally energy gets transferred to smaller scales. Right? I mean, when you actually stir your coffee, you expect the large scale eddies that you generate to form smaller scale eddies and smaller scale eddies and eventually get dissipated. You don't worry about that swirling that you generated becoming so large that it covers the whole cup and maybe spills water out. Here instead, you're in a system that supposedly naturally tend to push the energy towards larger scales. Indeed, the real champion, I think it's fair to say, of this kind of thinking, they really pushed it to use it to deeply understand properties of the ocean and atmosphere, is Isaac Held, And we try to follow very quickly his argument without going into the details. But he essentially appeals to this idea of energy transfer across scales. And now let's start phrasing the problem. This is the problem that we want to solve. We want to know what is the heat transport in this problem. What we mean is, again, you remember, is v theta, the meridional velocity times the temperature. In this problem, v is the meridional velocity, and it's given by a string function. You remember now we have two string functions, one has to do with the barotropic flow and one with the baroclinic flow. But the one with the barotropic flow is just the psi dx times tau, the temperature in our fluid. The other one will be the tau dx, the velocity associated with the baroclinic flow. But the tau dx times tau, now I'm taking an average over the whole domain. The tau dx times tau is just the dx of tau squared over 2. It's just a full derivative. So if I'm integrating over doubly periodic domain, that integral vanishes. So it tells me that it's only the barotropic flow acting on the temperature that transport heat in this system. But this is the full heat transport. It's these barotropic eddies that we described that are moving around fluid temperature around and achieve the heat transport. And so what we want to do in the theory is to see whether we can relate this heat transport, which is the quantity we want to know, in terms of the mean temperature gradient. And we said that the heat transport typically tries to reduce the temperature gradient, right? We started with some tilt in the interface and the Baroclinic instability was trying to slump it down. So we're just saying, well, the guess we make is that the heat transport is minus some positive constant d, we're going to call this an eddy diffusivity, times the mean temperature gradient. So that the flux is always in the direction opposite to the mean temperature gradient, and d, we don't know what it is, and that's what the theory should tell us. It's just some functional. The only thing we expect it to be is negative, is positive definite. Turns out that the tau dy, we know is the temperature gradient, but it's also the thickness gradient, if you want, the h dy temperature. Here is the thickness gradient, and the h dy is the tilt of the interface. So it's also related to the shear of the flow because they're in thermal wind balance, the capital U. So if you want, you can just write Ty is just minus U. And so this is just saying that the heat transport, we want to express as some function D that we need to find. The theory should be for D times U, or if you want the diffusivity, just the heat flux divided by that shear that we impose. So if you want the diffusivity, it's just a rescale the heat transport in this problem. And generally the way we would argue and the way we will follow is that we want to express the diffusivity, which is the rate at which mixing is transporting heat across latitude. That's what drives the heat transport. And if you look here, this diffusivity actually has the dimension of a velocity times distance, meters squared per second. So why would we expect D times L? Well, think about this is diffusivity D is measuring the rate at which you mix a fluid. So think about you trying to mix milk in your coffee cup this morning, right? You know that you can, if you want to accelerate the process, you could decide that you're choosing a particular size of stirring and you just stir it faster and faster. You expect if you go faster, you'll probably mix the fluid faster, right? So that diffusivity probably depends on the velocity at which you stir. But the second thing that you know is that if you use a toothpick and you try to mix on a very small scale, and no matter how fast you go, it's going to be hard to mix very efficiently. Actually, you want to stir on a pretty large scale. So that diffusivity should also depend on a mixing length scale of some kind, how wide a stirring you're willing to make. So indeed, the diffusivity depends on these two parameters that need to be determined because we don't know what they are. But we definitely can estimate them, for example, in numerical simulation. V, the velocity, is just the RMS barotropic velocity, right? In this fluid, because this is emergent spontaneous, you don't choose it, it's the instability that does, and we have to figure out what is the RMS velocity of this barotropic eddies that we've seen. The mixing length scale, well, we can figure it out from this schematic what it actually is in a turbulent fluid. The dashed line would be your mean temperature gradient at equilibrium, right? When we start, we just had a tilt at the interface or tilt in temperature, so there are, if I draw contours, the temperature is just increasing with latitude. And now the blue line is representing a big barotropic eddy that stirs that temperature gradient. And so what it does is going to deform the temperature gradient that we had at the beginning and create these meanders, right? It's pushing it down on this side and up on that side. And how strong of a temperature anomaly would I get at this point here? Well, the temperature anomaly tau prime here is proportional to the original temperature gradient times L, how much I displace this temperature isoline, right? You see that I'm displacing an isoline, and so essentially, if I take the temperature gradient times the distance over which I mix, this is how much the temperature has changed at that point, right? I have a gradient and multiply by the distance, I get the anomaly. So tau prime is just this LTY. So if I want to know what is the mixing length scale L, well, I need to know what is the RMS temperature produced at any point by the turbulence divided by the mean temperature gradient. And again, the RMS temperature is just T squared, tau squared, which I could estimate from a numerical simulation. And the mean temperature gradient is just the shear. So these are two quantities that at least I can measure in a fluid, but that I like to predict. Because if I can predict them, I have a theory for D. And if I have a theory for D, I have a theory for the heat flux, which is what I wanted to know. In this particular problem, as I said, we also need some drag to equilibrate the problem. So very often I'll use non-dimensional variables. So the diffusivity, I can non-dimensionalize it in terms of the only dimensional variables that I say matter in this problem, which are the shear and the deformation radius. So since it's meters squared per second, I divide by u lambda. And so this star, when I have a star, is going to be a non-dimensional diffusivity. You can just use those two dimensional parameters. Here, the only two dimensions that enter in the problem are always length and time. And so with these two variables, you can non-dimensionalize all the variables that enter in the problem. And we also have a mixing length scale L. I can normalize by the deformation radius. So this is a non-dimensional mixing length scale. And then I have, for example, for quadratic drag, mu star has dimension of 1 over length scale. So mu lambda is the non-dimensional version. So every time you see a star, it just means that it's the non-dimensional equivalent of the dimensional variable. So the way the classical literature approaches this problem, what time is it? This is telling me something. Ooh. Maybe I have to really accelerate. The way generally this problem is described is that if there is energy coming in, I have to put some energy flux into the problem. Baroclinic instability is extracting energy at some rate, and then dissipation is extracting energy at the same rate. All these energy fluxes have to be the same because this is the flow of energy. It's like the flow of water in a river. This is the source, this is the conversion, and this is eventually the sink in the sea. All those fluxes have to be the same because you cannot lose energy. It has to be conserved overall. And the argument of Isaac Hell essentially is then to try to get estimate for B and L using these two arguments. One is that I know what the energy extraction rate in baroclinic instability is because it's proportional to this horizontal, to the heat flux in the problem. Now the details don't matter, just accept that. I know what is the rate at which energy is extracted, and it's dependent on this D, U, and L. These are all variables I know, and D is what I want to know. But the second point, and he's going to say, well, this energy extraction then has to be equal to energy dissipation. And so this is the statement that he's making. But then he needs a second law, independent, because he has two independent variables he has to estimate. And the second law is just this it's just this idea that energy has to be conserved along this path as energy is transported to large scale. And if you've seen turbulence law, this is essentially the equivalent of Kolmogorov's law in an inverse energy cascade instead of the forward energy cascade, but it's the same argument. It says, well, V has to be proportional to the energy flux times the length scale. This is just a dimensional argument. It doesn't matter what it is. But if you use these two arguments, and this one requires an energy cascade, so how energy is transferred across scales, well, you can predict what the diffusivity is in terms of the dimensional parameter, because now you have two equations to construct V and L in terms of external parameter. And it turns out that the diffusivity of the non-dimensional diffusivity should depend as mu star to the -2. That was a prediction made by Held in 1999. Held is a brilliant scientist, so he already realized that. However, when he ran simulation of this problem, so this is now the non-dimensional diffusivity, and this is the length scale. So now we are running numerical simulation just to see how the diffusivity scales as a function of this drag coefficient at the bottom. That is one of the predictions that Isaac Held got. The squares are the numerical simulations. They line up along this line. This is the prediction that Isaac Held made based on that argument. And this instead is a D star that scales mu star to the -1. Clearly, that scaling doesn't seem to capture the dynamics of this system. So that scaling argument based on spectral description doesn't seem quite to capture the evolution of this system. So now we want to revisit the problem. I'm going to go fast, but I think what you have to get here is the fundamental concept, not the details. We are again describing the same problem. We are using the same approach. We're going to consider a linear and quadratic vector. You'll see in a second why, just to finesse the discussion. But we are going to take a very different approach in how we look at the problem. We think that looking at spectral space was actually a bit complicating the problem because, as I said, what really looked like what we were dealing with was a gas of vortices, right? Individual vortices moving around. So each vortex, since it has a vorticity associated with itself, can be characterized by what we call the circulation. If you want, that is the integral of the velocity along the contour of your vortex. Or if you want it, just the characterization of the spin, how fast the angular momentum, angular velocity of that vortex is. This gas is definitely described by the intervortex distance. This is the distance between vortices. And the velocity, then it's easy to compute how fast does the vortex drift around in this fluid if I characterize this way. Well, if I have a vortex with a compact circulation, the velocity v goes as gamma over r. The circulation over r, that's a Rankine vortex, how it generates velocity away from its core. Well, but this vortex, therefore, a vortex cannot advect itself. It cannot advect other vortices because the velocity around itself is axisymmetric, so it doesn't move itself. But this vortex, for example, is going to advect this other vortex. If it's positive vorticity, is going to advect it around in this direction, and its velocity is going to gamma times the intervortex distance, because that's how distant that other vortex is. So that's the r, the distance from the first vortex. So given gamma and LV, I also know what is the RMS velocity. And one of the surprises in this simulation is very clear that at equilibrium, the vortices have always a scale pretty much close to the deformation radius. They don't get much larger. If there are experts in the room, you'll see a lot of literature that insists that the peak of kinetic energy in this solution is larger than the deformation radius. That is actually true, but that has a lot to do with what is the spacing between vortices, because that's a bulk measure that tries to look not at a particular vortex individually, but if two vortices come close together and rotate around each other for a while, that looks like there is energy in the larger structure, but the two vortices are still separate. So the scale of the vortices themselves really doesn't seem to change much. So there isn't what would have been called this inverse energy cascade in a strict sense. We don't see vortices really deforming each other in this two-layer problem. There is the one-layer problem, again, for the expert in the room, which is very different and apparently behaves differently, but that's not a surprise, because here the whole focus is on baroclinic instability. And in one-layer problem, since you cannot have a tilt of an interface, there is no baroclinic instability, so it's a very different question. So in order to solve the problem now, we have a slightly different set of questions. Well, first of all, we need to know, we want to find a scaling for the diffusivity, so we need a scaling for V and a scaling for L, the mixing length scale. Well, it turns out that at least L is also equal to the intervortex distance. Think about a particle here, not a vortex now, some blob of fluid around here that gets advected, being mixed around, like a dye, some blue spot. Well, it's going to be advected by this, the velocity induced by this vortex until it hits another vortex, and then it starts moving in a different direction. So the mixing length scale, how far do you mix before you interact with another vortex, is the intervortex distance. So this scales with that. So now, at least one of the variables has been eliminated. So now we need scaling for the mixing length scale L, which is also the intervortex distance, and the RMS velocity, much like in the problem that Isaac had produced. When you want to know what is the velocity, this RMS velocity I was describing, that is transporting fluid around, think about two vortices. Here there is a temperature gradient. This is, for example, warm water, and this is cold water, north here, or warm air and cold air. These two vortices, in this particular example, have opposite sign. So they are advecting fluid, right? They are both advecting fluid upward in the middle and pushing fluid down on the side. The velocity that matters is the velocity halfway between the two vortices mostly. If I look at what happens very close to the vortex, there is no transport at all, right? There is nothing in transporter because the velocity is just so strong, it just wraps you around the vortex. It just rotates around the vortex. So if I just move around the vortex, I don't transport any heat or any tracer. It's only when I'm, let's say, halfway through the distance that I really experience a velocity that pushes me away. And then indeed I take, for example, this red warm air towards the cold direction. This might seem like a trivial statement, but it's not trivial for the second point I'm going to make, and given the time, I'm not going to go through the argument, but just point what is the big difference. The first part We need, again, two scaling laws because we have to parameterize the dependence of our diffusivity on V and L. So we need two scaling laws that relate V and L to the dimensional parameter imposed in the system. In this case, deformation radius, shear, and drag possibly. The first statement is just that the rate at which you release energy through Baroclinic instability is equal to the barotropic kinetic energy into the system. That's a bit like the argument of Salmon and Helbrecht. I mean, there is baroclinic energy that transfer energy from the baroclinic potential energy to the barotropic kinetic energy. So that's fine. But the one that is very different is the second one. Again, this is the extraction of potential energy has to be equal to the dissipation of energy, right? You remember that was the second part of the plot that said, well, the energy is released, but then it has to be dissipated. Now, why is it different? We're not going to go through any of the detail. Let's just point what the difference is that the point vortex has the maximum velocity right in the center of the vortex, not on the side of the vortex. So if I ask where the dissipation, which depends on u squared or u cube, is, well, that dissipation is much larger than what you might call mu u squared, right? It's the velocity that is being dissipated is not the velocity in between two vortices, it's by the velocity in the core of the vortex. We said the velocity goes as gamma over r, becomes very strong in the center of the vortex. So as the vortex is spinning, all its dissipation is right in the core of the vortex. But the velocity that is affecting the fluid and contributing to heat transfer is the velocity at distance LIV, a distance intervortex distance away from the vortex. Those two velocities are very different. That's generally what is conflated in previous theory. And so, for example, the u squared, I'm saying it's v squared, the velocity squared, the RMS velocity squared, but multiplied by log L star. L star is the intervortex distance, non-dimensionalized by lambda, if you want. And that's a very large number because we said the vortexes are spread out. They're not very close to each other. So L over lambda is a large number. So this is a different scaling that has to do with the fact that dissipation is associated with the core of the vortex, not with the typical RMS velocity. And that's a fundamental difference when you look in real space. That's something that would be hard to capture in a spectral description because, you know, a vortex is a structure that you can see in dimension in real space, but in spectral space, you generally lose all information about phases. The fact that vortex is a coherent feature. And if there are space in between vortices, something you don't see anymore in a spectral description. So now if we use the scaling that I proposed, now we can predict the scaling for the diffusivity and the mixing length scale, both for linear drag or for quadratic drag. For quadratic drag, you already see that the d star depends on 1 over mu star. So we start getting the scaling that we described before. We get a very funny scaling for d star as a function of the linear drag. It seems to depend exponentially 1 over kappa star, where kappa is the drag coefficient. That's a very non-trivial scaling if you want one. Turns out that Thompson and Young in 2007, two oceanographers in this case, had already derived empirically this scaling by just looking not at numerical simulation and just saying that if you want to fit the dependence on the drag coefficient, it seems to be very non-trivial and it has a form like that. They didn't have a theory, but they contended that that's what it should look like. And indeed, we can then plot. Let's go directly to the diffusivities. Now, these are numerical simulation with a quadratic drag coefficient. These are the blue dots are numerical simulation with a linear drag coefficient. And you see that the theory is this blue line. The theory has two adjustable parameters, the arbitrary non-dimensional constant we have to fit, but the shape of this curve is clearly non-trivial. It's not, you know, it's clearly an exponential function of 1 over kappa star. So that is definitely independent of the choice of those parameters. And we see the theory seems to capture this very different dependence on drag coefficient, which, by the way, insists on the importance of the drag coefficient in equilibrated turbulence. So both in the ocean and the atmosphere, what happens at the boundary is going to be quite important. I'm going to finish, promise, quickly. I just want to show you that we can also do the full problem where we take the QG equation, but now we force them with heating and cooling. This is a pattern of heating and cooling. We are cooling in high latitude and warming at low latitude so that we're getting more into a system where now we don't prescribe the mean state, we just let it evolve. So if we force the system, we can now ask, well, can we predict what is the mean temperature in this system without knowing it, without having to solve any of the equations? Well, it turns out that as this is the same statement I made for the planetary atmosphere, the heating and cooling pattern has to be equal to the heat transported, the divergence of the heat transport in the system, meaning that if there is excess heating at low latitude and excess cooling at high latitude, that has to be balanced by heat transport, right? And I'm just rewriting that same budget. But now since I have a scaling for the diffusivity D, as a function of the parameters of the problem, I can just plug it back in here. And in theory, I can solve for what is the mean temperature gradient without having to solve anything. I just solve this equation because D will depend, according to our scaling law, on the temperature gradient, on the deformation radius, and on the drag coefficient. We know what is that dependent, so we can just try to plug in what we just solved for. And so this is now a fully non-turbulent solution. This is warm and this is cold, and you see that you develop a lot of eddies. And if I wait long enough and then I take a zonal average of this problem, right? So I look what is the mean temperature profile. This is the blue line. This is the equivalent, the effective latitude of your system. Here there is temperature increasing on this side and temperature. This is the temperature profile. It's increasing, decreasing, and increasing because of what the pattern we imposed here. And the dashed line is the prediction of our theory. All it knows is what is the strength of the cooling and the heating and what is the deformation radius. It doesn't need to know anything else. The non-dimensional parameters we are using are still the one that we used for the doubly periodic system. So we are not trying to fit any new parameter. We're just using whatever the closure was that suggested us. And now we're looking at this non-homogeneous problem. But we can predict exactly what is the temperature, very close to exactly what is the temperature profile of this system. We can do it for linear or quadratic drag. Again, we can predict exactly what the mean temperature profile. So in a sense, for this very simple problem, admittedly, of two-layer QG, but with a non-trivial forcing, you have essentially a closure for the climate system of that simple denominator, that simpler model, because you're predicting what is the emerging temperature profile without having to solve the full turbulent system. Now, I'm not going to go through this, but we can also include effects that I haven't described so far. We have done the same problem in the presence of beta. What I mean by that is that so far we assumed that the system was rotating at a constant rotation rate. On a sphere, it turns out that effectively the rotation rate changes with latitude, because the rotation rate that matters in the equation we have written is the rotation rate normal to the surface as you look. So if you're at the pole, you feel the full rotation of the planet, but as you move to the equator, you feel less and less of it. And you can imagine that that rotation rate affects the angular momentum of your air column, because it's a different planetary rotation that the water column is rotating with. And so adding that term actually modifies the turbulence properties of the system. That's quite important, because we know that in the presence of beta, for example, the quasi-geostrophic turbulence forms very strong zonal jets. That's what you see in Jupiter. So it's a fundamental property of that turbulence. It turns out that the presence of beta does suppress the instability. Just put this here. Again, we can predict also in the presence of beta. This is the temperature solution. Oops, this one without beta. As you increase beta, the temperature gradient becomes larger and larger, because the eddies become more and more inefficient at transporting heat. So you're getting closer and closer to a limit where the eddies are not able to create a more moderate climate. The reason why we're doing all of this is that now that we have this scaling theory, we are trying to use them to parameterize, in particular, heat transport by ocean eddies in climate. In the atmosphere, this is useful more as a theoretical framework, but large-scale models generally resolve the macro turbulence, this large-scale cyclone and anticyclone, so you can just look at their effect, but just simulate it. The ocean, these eddies have scales that are order of 100 kilometers and a bit less, between 10 and 100 kilometers, depending on latitude. And so they typically fall on scale smaller than the grid scale of the large-scale climate model. So you have to represent their effect on the mean. So essentially, you have to do the exercise I've done here. You had to represent the heat transport by these eddies in terms of variables that are resolved by the model, the large-scale variable that the model sees. And so we're trying to use this scaling to parameterize the effect of turbulence in the ocean mean state, which is necessary in the end to get the large-scale equilibrated climate system. And I'm sorry that I went long, but I guess I was too inspired at the beginning. I should have cut shorter. Interestingly, now when I rehearsed the talk, I was going too fast.